Welcome to Bioengineering Basics. My name is Amy McLeod, and I'll be providing a bit of an introduction. I'm with the Alberta Riparian Habitat Management Society, more commonly referred to as Cows and Fish. Before we get started, this session is being recorded. And please keep yourself muted throughout. If you have a question, pop your question in the Q&A box, not the chat box. And all questions will be addressed at the end of the session. I am joining everyone today from Calgary, Alberta. And in the spirit of respect, reciprocity, and truth, we honor and acknowledge that we live, work, and play on the traditional territories of the Blackfoot Confederacy, the Siksika, Kainai, and Piikani, the Tsuut'ina First Nation, the Stoney Nakoda First Nation, and Métis Region 3, and all the people who make their homes in Treaty 7 territory. There are many others joining from across Alberta and other places as well. So please take a moment to acknowledge the many First Nations, Métis, and Inuit whose footsteps have marked these lands for centuries. That long relationship includes both experience and knowledge gained, and a deep and strong sense of connection with the land and water. Cows and Fish has been working in collaboration with Bragg Creek Trails, the Elbow River Watershed Partnership, Alberta Environment and Parks, and local ranchers to enhance watershed health and resilience in the Bragg Creek watershed. This collaborative was initiated by Bragg Creek Trails and has been supported through the Watershed Resiliency and Restoration Fund through Alberta Environment and Parks, and by the cumulative efforts of many volunteers. We are pleased to work with Kerwood Lytle to present a lunch hour bioengineering webinar, which is a precursor to a restoration field day taking place on Friday, October 8th. The event this Friday is full. However, you can visit the Bragg Creek Trails webpage for upcoming volunteer events, or the Elbow River Watershed Partnership. You can also check out Cows and Fish's webpage or follow us on Instagram or Twitter. As I mentioned before, I work for an organization called Cows and Fish, and you may be wondering what cows have to do with fish or restoration and trails in general. The answer is in relationships and understanding relationships. In this case, the relationship between cows and fish, or cows' impact on the landscape, and water. But it isn't just the relationship between cows and fish. There are many different human activities that impact our land, and as a result, the water. We recognize that fish aren't just a product of the water, they're a product of the entire watershed, which includes the land and us. The physical description of a watershed is a drainage catchment that channels snow, rain, and groundwater into a common location, such as a stream, lake, or wetland. But a watershed is much more than that. It contains history, culture, and decision-making. And no matter where you are on the landscape, we are all part of a watershed. All of our activities add up to impact the health of our water. Riparian areas, the areas that connect land and water, provide clean water, flood and drought resiliency, provide recreational opportunities, and are beautiful places to see and visit. Cows and Fish empowers people who live, work, and play throughout Alberta to care for these riparian areas. We work with many partners to provide learning and on-the-ground opportunities. Together, our actions make a difference. And so without further ado, I would like to introduce our presenter, Mike Gallant. Mike is a water resource engineer who's been working on the planning, design, and construction of river engineering, water resources, and stormwater management projects since 2004. He has a wide range of specialist expertise, including hydrology and hydraulics analysis and modeling, stormwater modeling and design, ground bioengineering, fisheries habitat design, and erosion and sediment control. Mike received his Bachelor of Science and Masters of Science from the University of New Brunswick, where he specialized in the ecohydraulic design and construction of fish habitat enhancement structures. And I'll invite you now, Mike, to share your screen and begin your presentation. Thanks.
Hello. Yeah, there we go. Hello, everyone. Just a few buttons I needed to click there to get started. Thank you for that great introduction, Amy, and also thank you to Bragg Creek Trails and Cows and Fish for allowing me to present at this wonderful webinar event and take part in the activities on Friday. And also thank you to everyone for attending this webinar. I'm going to turn off my screen just to save some bandwidth. Sorry, turn off my video to save some bandwidth, and we'll get into the presentation here. Okay, so let's start today by going over the objectives for this webinar. At the end of this session, I hope that you will understand what bioengineering is and when it can be used, have a grasp of the environmental benefits, gain basic knowledge of the techniques, see examples of projects and what was learned from them, then ask some great questions at the end of the presentation. To meet these objectives, these are the topics that I'll be covering with you today. Just a quick introduction to me, more so a little bit more detail than what Amy provided. What is bioengineering, bioengineering history in Alberta, the materials that are used, the site considerations, plants, and then the techniques and some case studies. So very briefly, I've been working for a consultant for the last 14 years in water resources engineering. As mentioned, my expertise lies in fish and habitat enhancement, riverbank erosion protection, flood protection, erosion sediment control, and but more specifically, of course, soil bioengineering, where I've been working since I started my consulting career. I've also been part of some incredible project teams who have delivered some award-winning projects. An example shown up on the top right here called the Bow River Bioengineering Demonstration and Education Project. I'm also involved in the City of Calgary Repair and Monitoring Program, where we are conducting long-term monitoring on over 60 bioengineering sites in Calgary. Before we go further, let's briefly define what bioengineering is. A very simple definition is that soil and water bioengineering is the use of living plant materials to perform some engineering function. Typically, bioengineering is used for riverbank erosion protection or to stabilize eroding slopes. So you'll note that I have soil and water bioengineering here listed here, because if you search for bioengineering in Google, you'll get back a whole lot of more the medical side of bioengineering. So there's a few terms that are usually placed in front of bioengineering, such as soil or soil and water, that more define it for what we're talking about today. It's important to note that bioengineering approaches aren't new. For example, Chinese historians recorded the use of bioengineering techniques for dike repair as early as 28 BC. Bioengineering has been documented in Europe since the 1600s. The Acadians were building bioengineering structures such as living dikes, known as aboiteaux dike, and sluice boxes in the 17th century in the east coast of Canada. And there's documented use of bioengineering techniques in the US since the early 1900s. So we're on a bit of a path of rediscovery here, where we again realize that bioengineering approach helps us achieve the goal of reestablishing a native plant community that will provide permanent erosion protection and stabilization that can self-repair and regenerate and achieve habitat, biodiversity, climate change, cost, and aesthetic goals. Ultimately, a good bioengineering site will allow natural processes for recovery to take over. I've done a bit of research into the history of bioengineering in Alberta. It's by no means complete, and you might have some names or events to add here, but I thought I'd share the key bits that I've learned so far. It appears that reclamation and restoration using bioengineering methods were introduced in the 1970s in Alberta. A key figure of this era was Nick Horstman from Western Canada Erosion Control, who was doing reclamation work in coal mining areas of Alberta. In the mid-1970s, he developed a relationship with Dr. Hugo Schechtel, who was an Austrian soil bioengineer, and who was one of the most influential figures in the modern era of the practice. His writings remain some of the most important works in the English language. Dr. Schechtel came to Edmonton to visit Nick Horstman in the late 1970s, and then it was thought that they came up with the idea to translate some of Schechtel's work and other important European soil bioengineering's work into English. And this became Bioengineering for Land Reclamation and Conservation, which was published by the University of Alberta Press in 1980, and is a key text for bioengineering in the English-speaking world. The pipeline industry was also an early adopter of bioengineering to repair watercourse crossings. A leading edge pipeline watercourse crossing course, a manual that featured bioengineering techniques, was developed in the early 1980s by the Petroleum Industry Training Service, and in part delivered by Pisces Environmental, that ran until around 2006. Attendees came from across North America to learn about bioengineering, and the course was presented to several large pipeline companies in the US and to the US Federal Energy Regulatory Commission in Washington. Now, getting back to Dr. Schechtel, he also influenced a young Robin Sautier. So Ms. Sautier was from Edmonton, and after completing a landscape architecture degree from the University of Guelph, went to work with Dr. Schechtel under a soil bioengineering apprenticeship from 1976 to 1981. Her company, the Soil Bioengineering Corporation, which is now known as Robin B. Sautier and Associates, designed a bioengineering demonstration project with Alberta Transportation and Utilities in 1986 in Kananaskis. Ms. Sautier went on to have a long and successful career as a soil bioengineering specialist. She's still working and contributed to several key bioengineering manuals and texts, including co-writing this book with Donald Gray in 1996. Throughout the 1980s and 90s, the consulting industry and Alberta government departments incorporated bioengineering approaches into fish habitat and erosion protection projects. The Fish Habitat Enhancement Design Manual that's shown here was developed by Alberta Environmental Protection and Pisces Environmental back in 1989. Through the 90s and the 2000s, other key players in the field emerged, including David Polster, whose designs are often used for drastically disturbed sites, and John McCullough, who developed biodraw, erosion draw, and dirt time, and also designed demonstration sites on a few rivers in Alberta, including the Pembina River in 2005 with Alberta Transportation. Then a few bioengineering projects emerged in Calgary after the 2005 flood, including a timber crib wall at Sue Higgins Park that withstood the 2013 flood and inspired a bit of a timber crib wall craze in Calgary after the 2013 flood. The City of Calgary also developed bioengineering design guidelines in 2012 with AMEC, Cows and Fish, and Pierre Raymond from Terra Erosion Control that were released just in time for the 2013 flood. Now, after the 2013 flood, where in Calgary over 35 kilometers of riverbank were damaged and there was significant risk to critical infrastructure, there was one might consider a rediscovery and a resurgence in the use of bioengineering techniques to stabilize eroded riverbanks versus the conventional hard engineering approaches like rock riprap. Before the 2013 flood, there were 6 known bioengineering projects in Calgary. Then after the 2013 flood, there were over 50 projects that have been constructed. So the history of bioengineering in Alberta spans over 50 years and is filled with some of the biggest names in the industry. So how does soil bioengineering work? Capitalizes on the very important role that vegetation plays in controlling erosion. So there are 4 key ways that vegetation controls erosion. The first is soil reinforcement, where the root system physically binds or restrains soil particles to transfer shear stresses in the soil to the resistance in the roots, while the above ground residues will filter sediment out of rain and stormwater runoff. The second is near surface velocity modification, so changing the velocity on the surface where stems and foliage increase surface roughness and slow velocity of that runoff or flow in a stream. The third is soil moisture modification, so it's transpiration and interception by the foliage that limit buildup of soil moisture stress, and then roots and plant residues help maintain soil porosity and permeability. The fourth is buttressing and arching, where the anchored and embedded stems can act as soil nails or buttress piles or arch abutments in a slope and counteract shear stresses. Also very importantly, the resulting stable bank allows for the establishment of volunteer plant growth and subsequent vegetation succession. Now, bioengineering offers several benefits, including stability. So it improves slope stability, protects against surface erosion, regulatory, smoother and quicker environmental approvals. When it comes to ecological, it improves riparian habitat, cover, nutrients, temperature, wildlife passage. Economic, it reduces long-term maintenance costs, and social, improves aesthetics by appearing more natural. With respect to regulatory processes, for someone who does submit these applications like I do, this is an important consideration that bioengineering offers several advantages over conventional approaches such as riprap, where bioengineering has lower risk to fish and fish habitat. There's lower complexity of fish habitat assessment needed to support a regulatory application, a shorter duration of project review, and a lower amount of offset required by DFO. Additionally, some jurisdictions, such as the City of Calgary, require that bioengineering approaches or justification as to why they have not been used. Another key consideration regarding bioengineering is that it draws on the experience and knowledge of several disciplines. An example of the nature of bioengineering, or the interdisciplinary nature of bioengineering, is shown in this slide. So now this is an example of the team that was needed to deliver a large bioengineering project in Calgary. The expertise and disciplines needed to accomplish the project are shown in this bubble diagram. So as you can see, the projects are very interdisciplinary in nature, with design and engineering shown in blue, biology, environmental shown in green, and then stakeholder engagement and regulatory approvals in purple. While this may not be needed for all projects, particularly smaller projects, it's still important to know what types of experience might be necessary to deliver a successful project. So now, all that good stuff said, there are some limitations to the use of a bioengineering approach. Now, it's not suitable for all sites. A good example is areas with significant geotechnical concerns, as shown in the graphic in the top right, where there's a deep-seated rotational failure, or significant erosion issues, as shown in the photo in the middle right. So periodic monitoring and maintenance of a bioengineering site may be more often initially than traditional methods, or at least until the vegetation establishes. There are also important considerations when living vegetation is incorporated into a design versus inert construction materials. For example, vegetation is susceptible to drought and will likely require irrigation, or will require irrigation in arid locations like southern Alberta. Soil conditions are also important, where conditions that are toxic or inhospitable to vegetation will likely result in low project success. So the project on the bottom left shows a dead cutting that was planted in anoxic or low oxygen soil conditions. Site aspect and shade conditions also affect vegetation success. So the project in the middle picture here shows a site with a southern aspect, so very warm conditions combined with the rock, which will trap heat. And there's a soil cigar that was planted with live cuttings that with this very low success of the live cuttings in that soil cigar. Grazing and trampling can also limit vegetation success. So now that we've covered what bioengineering is and its benefits and limitations, let's discuss what we need to know about a site when planning a bioengineering project. Firstly, it's very important to develop a good site-level understanding of the conditions and processes occurring at a site, so that an appropriate solution can be identified that will properly address this erosion problem. There's nothing worse than spending a bunch of money to fix a problem to have the problem pop back up again. So now, bioengineering project planning starts with having a good understanding of a good understanding of the objectives. So you might ask yourself, what is this project attempting to achieve? Is it stabilizing erosion in a creek or stream or on a slope? Or is it for habitat or riparian health enhancement? Is it aesthetics? Or is it mandated by a regulator? It could be a combination of all of these. Defining clear project objectives at the outset, at the start of the project, allows for the development of appropriate solutions, and then also allows to evaluate the success of that project at its completion. So next, it's important to gain a good understanding of the site conditions and factors that could limit the success of a project. For example, what might limit the growth of vegetation at the site? Aspect, precipitation, soil moisture regime and groundwater seeps, existing vegetation and weed species, existing erosion, wildlife browsing or trampling, human or dog use, vehicles, boat use, etc. Understanding the large-scale geomorphic and geotechnical processes occurring at your site helps to identify why instability is occurring and what the erosion mechanism is at the site. And now, determining what processes are occurring at the site will help to gauge whether bioengineering can be used, such as the example shown in the previous slide there, or not, and also what techniques should potentially be used. Gaining an understanding of the general hydrology at the site, including quantity of precipitation and the overland runoff or stream flow patterns, allows the calculation of hydraulic parameters that quantify velocities and erosive forces acting at the site, which can then be compared to the possible approaches that you might be thinking about to remedy the erosion issue. Since we are using vegetation as part of the approach to control erosion, an understanding of the existing vegetation species at the site helps to inform the species that are selected for the design. So noting the species that are found naturally at the site should form part of a site investigation. In particular, shrubs and tree species should be noted that have adventitious properties that we'll go over later here. For stream or riverbank projects, the vegetation trim line or the lowest line of permanent woody vegetation should be noted and used as the level where woody vegetation begins in the design. For slope projects, we should look carefully for signs of vegetation stress due to soil movement or excess moisture. More generally, it is a key part of bioengineering approach to have a good understanding of best practices for the harvest, transport, storage, soaking, installation of live cuttings, and care and installation of container plants, but also plant installation scheduling, irrigation, and weed identification and removal. Once the background data is collected and approaches are starting to become more clear, then it's time for to consider their constructability and cost effectiveness. These factors are often used to evaluate different options to help select a preferred one. Considerations here would be things like access, minimizing disturbance in sensitive areas, project sequencing, and issues related to wildlife and or fish restrictions on construction scheduling, material availability and cost, equipment and labor requirements. Then considering the post-construction monitoring and maintenance requirements helps feed back into the planning process as key components of a monitoring and maintenance program, such as program length, approach to fencing, irrigation, and weeding, may influence how the project will be designed and will allow the evaluation of the success of a project against the clear project goals that we discussed at the beginning here. I thought it might be useful to go over more specifics on what a site assessment should cover using the West Bragg Creek site that we're working on Friday as an example. So things that we'd want to document when we are looking at a site are, firstly, to confirm and verify the project goals. So for example, if the goal is to stabilize an eroding slope, it's important to verify, that a bioengineering approach will work, or that it is needed based on how the natural system is responding to the disturbance. The water flow patterns in the creek or stream or overland flow patterns, particularly the flow direction based on the site topography, and if you can get a sense of the volume and potentially the inundation duration. The presence of any seeps or groundwater issues should be noted. We'd also want to take a look at undisturbed areas to get an understanding of how they are functioning and possibly use our observations to support a design. Erosion features such as bank erosion, surface rilling, gullies, and slope instability and the potential causes should be noted. Existing vegetation species and the distribution at the site, also noting the vegetation trim line, as mentioned previously, if the goal of the project is riverbank erosion. We'd also note invasive species and insect damage on the native vegetation that may be a concern for our treatment in the future. We'd want to note the aspect to observe how warm the site might be and also shading potentially for buildings in an urban setting or existing vegetation in a more natural setting. We want to note soil conditions such as low oxygen, saturation, clays, toxic conditions, etc., that might affect vegetation establishment. So in particular, we'd look for evidence of soil compaction. So this yellow polygon here shows the old shell road, and within that polygon, the soils are very compacted because of that road construction and use. We want to note human and wildlife activity. So we're looking for trails, either formal and or informal, and trampling and browsing. We'd also want to consider the available space to construct so that we can get equipment or materials or people in the site safely, both into the site and out of the site safely. And also what kind of access the site is available to the site for equipment if needed, but also for any observable, we want to look for any observable overhead or buried utilities if we're doing some digging. So now we'll talk a bit more about the materials that are used in bioengineering. So the key aspect that differentiates bioengineering from conventional erosion protection or stabilization is that living vegetation is used. So there are several types of vegetation that are commonly used in bioengineering that include live cuttings up in the top left here. They are the main materials used in soil bioengineering construction and are lengths of live branch or stem materials that are harvested from living shrubs and trees during the dormancy period. They have adventitious growth properties and so will root when embedded or inserted into the ground. The second type are rooted plants, and those are plants that are pre-grown in a nursery to common sizes such as 1 gallon, 2 gallon, 5 gallon, or 10 gallon pot sizes. In bioengineering projects, they're typically used for species diversity or to revegetate areas that are not exposed to flowing water. Also, the species that are used as rooting plants typically do not root from cuttings. although they can, depending on how you select your species. So tall-rooted stock, these are relatively new vegetation stock consisting of live cuttings that have been grown out in a specific manner to have roots at the base and then leafed out at the crown. They are used for construction in late summer and early fall when traditional live cuttings would no longer be dormant and should no longer be used until the dormancy period opens back up again in September, late September, early October to March. Plugs are a seedling that was sprouted and grown in a small cell. They are often grown together in a large tray with many cells. Plugs are used in a similar manner as rooted plants, but since they are much smaller, they are cheaper and many more can be installed for the cost of one container plant. And seed, which are typically grasses and forbs for ground cover, but they also provide some that also provides some erosion protection at low velocities. So the most common species used in bioengineering are from the willow and poplar families. And the main reason for this is that these species have several beneficial properties for use in bioengineering. They grow in most moist soils of riparian areas and wetlands. They are resilient to high velocity floodwaters, burial by sediments, long periods of inundation, and high winds. One of their coolest properties is that they root from cuttings, as I mentioned previously, because they have adventitious buds with flexibility to form roots when in contact with water or moist soil. So adventitious buds are buds that develop in an atypical place rather than at the branch tip or in the leaf axils. So along the stem, for example, is shown in the photo on the right here. This strategy is super helpful in disturbance-prone environments such as riverbanks, where flooding or erosion or beaver activity can cause a branch to become dislodged or float away and flow down the river, where the stems can then readily root in the muddy riverbank. For bioengineering projects, we can use this property by harvesting and installing cuttings during the dormancy period, when the cutting has its highest amount of stored energy that can be then used to grow new roots and shoots within the growing season without the ability of photosynthesis. So that's super cool, I think. But also, in fact, live cuttings have been shown to grow more in a year on average than container plants. Also very cool that some species can grow new plants by suckering from root systems. So they end up establishing in bare areas that were not previously planted, as shown in the middle photo here along the bottom. And in effect, that's similar to coppicing. Some species respond positively to browsing. So when a plant is eaten or by a deer or beaver, a chemical signal is interrupted and the lateral and adventitious buds are stimulated to grow. It's not uncommon to see upwards of 5 to 10 new branches growing off a main stem that has been chomped on by wildlife. The result is a very bushy shrub. It's important to note that this will only occur when the root system of a plant is well established. So speaking of roots, what do they actually look like when they are established? So here are a few photos that show how the roots from cuttings will grow around soils and rocks to bind them together to provide highly effective soil stabilization. The photos on the top left show root growth in a seven-month-old stake, and the photo on the right shows the growth of red fibrous roots at the water's edge around native gravels and cobbles, about 1 meter or so away from the bioengineering structure. These photos show that the roots will stabilize soils both immediately around a live cutting, but that they can also make their way around native soils to access water and nutrients and have a much larger zone of influence. The photo in the lower left, and to a lesser extent, the photo on the lower right, shows how roots will grow around rocks and through narrow crevices and then regrow back to their original size. This is important to understand this property, since it's commonly thought in engineering circles that roots will grow to the same size the whole length, and they will displace rocks and cause damage to erosion protection structures, where that may not be the case as shown in this photo. Now, with respect to the above ground portion of the plant, so what we actually see, the shoots, they have beneficial properties for erosion protection as well. They are flexible and resisting and create increased roughness at the soil surface. They increase shear strength resistance, and they provide habitat, shade, cover, food, and nutrient inputs for aquatic and terrestrial wildlife. They improve water quality filtering and uptake of pollutants. They reduce water quality in small streams, et cetera, et cetera. Lots of good benefits there. The bottom photo shows, the bottom photo illustrates a case study on the ability of the planted vegetation to reduce erosion force from flowing water at the surface. So the photo on the bottom left shows a low bench that was planted with live stakes at a location in a river that was undergoing significant erosion. And the bench was overtopped several times the following winter, a few months after construction, as shown in the second photo. But instead of continued erosion at the site, the vegetation attenuated velocities and helped to trap and hold sediment on the flood terrace, as shown in the third photo here. The last photo shows how the project looked a few years post-construction. It has established quite well. It's important to note that for erosion control, soil stabilization, and plant establishment, we are striving to achieve an appropriate ratio of the below ground to the above ground portion of the plants, what is referred to as the root to shoot ratio. One way to achieve this is by making sure to follow the harvesting and installation best practices that we will go over a little later in this presentation here. Depending on the conditions at a site, structural materials or non-living materials might also be required to support the living vegetation to withstand the erosive forces that are present. A common material used in bioengineering projects are rock, which shown here is several types of rock: blast rock, of a few sizes, rounded rock, random cobbles, gravel, and pit run. Logs are sometimes incorporated for habitat, either within a structure or on the surface, as we are doing for the West Briar Creek site. Timber is used for structures such as crib walls or dimensional timber. Matting is often used at a site for temporary erosion protection for either raindrop or flowing water erosion until vegetation establishes. There are a variety of matting products out there that are made from straw and or coconut fibers, and some with various types of plastic. What's shown in the photo here is a coir geogrid along the ground and a coconut erosion control matting being rolled out over top. Coconut products last longer and are more durable than straw. As you can imagine, plastic products last longest. So depending on what the project objective is, I would caution against the use of plastic products since they persist in the environment and pose an environmental hazard to fish and wildlife. There are usually fully biodegradable options that provide as good or better temporary erosion protection. Other temporary erosion control products, such as wattles and silt fences, are commonly used on bioengineering sites. Again, the purpose is to provide temporary stability until vegetation establishes. The products shown here are Curlex sediment logs that are made from aspen shavings in the top photo, and then the bottom photo is a compost-filled sock. The same goes for wattles as for matting. Try to choose a fully biodegradable option. Lastly is fencing, both temporary construction fencing as shown in the top photo, with the purpose to restrict access to a construction site that will keep both the workers and the public safe. And then the bottom right is a rodent protection fence to try to keep out wildlife. So especially beavers, but dogs too, until vegetation has a chance to establish. Okay, so now we've covered the materials that are typically used in bioengineering. Let's look at how they're put together into what are called bioengineering techniques. Each technique represents a different use of live materials and or non-living materials to address an erosion issue. So we'll start with the plant-based techniques, which are often referred to as soil bioengineering techniques. There are no or limited non-living materials used or included in these techniques. So the vegetation is solely being relied upon for erosion protection, with a small caveat that there is often matting used too. In most cases, these techniques can be constructed by hand without the need for heavy equipment. So the first technique in the top left is branch packing, which is used to repair small eroded gullies or slumps, such as the hole left when a tree is uprooted and washed away. Pardon me. It consists of layers of branches placed in a herringbone fashion, covered with soil, then secured with wooden poles and stakes. No excavation is required in this technique, and it can be completed manually. Brush layers I'll cover in a bit more detail in a bit. A brush mattress, the third here, is a layer of live cuttings placed on a bank or slope and lightly covered with soil. This is a superficial treatment that can be also be constructed entirely by hand, but because it's on the surface, this technique should be used where soil moisture can support vegetation establishment. This can be mitigated by placing the butt ends of the live cuttings deep enough into access groundwater. Wet toes is how this is sometimes referred to. We'll cover fascines, live pole drains, and live staking in more detail in the next few slides. A wattle fence is a short retaining wall on the far right here. It's a short retaining wall built of live cuttings. The idea is that the fences take up the vertical component of the slope and then reduce the effective slope angle and allow vegetation to become established within that structure. It's very important that wattle fences are used at locations where soil moisture conditions and aspect allow the live cuttings on the face of the fence to establish. This is particularly challenging in southern Alberta's dry climate, so I'd use this technique with caution. And now let us look at some living structures, also referred to as biotechnical techniques. For these techniques, a combination of living and non-living materials are combined to address erosion issues. In these cases, the idea is typically to either rely on the structural material to provide erosion protection with the vegetation meeting other goals such as habitat or aesthetics, or to rely on the structural materials to stabilize the slope or bank for a period long enough for the vegetation to take over the role of erosion protector when the structures degrade. In most cases, these techniques require more analysis and design and require heavy equipment to construct in comparison to the plant-based technique. The first technique I'm showing here on the bottom left is live slope grading, which consists of a lattice-like array of vertical and horizontal timbers that are fastened or anchored to a steep slope. The purpose of the structure is to support vegetation growth on very steep slopes that normally cannot be vegetated or that can only be vegetated with great difficulty. The second technique is a vegetative retaining wall, which is used to resist unbalanced lateral earth forces, retain earth and masses, and or to protect against scour and undermining. Typically, this type of wall is constructed so that the structural materials do the work and the vegetation is included for aesthetic and or habitat purposes. Vegetative riprap, the third technique here, is a layer of stone and or rock armoring that is vegetated. This is best done during construction versus coming back later and retrofitting the structure with vegetation after the rock was placed. Some techniques to add vegetation to rock are pole planting, brush layering, live staking, soil covering and planting, and void filling, then planting. The fourth technique here is void vegetated soil wraps, which consist of brush layers that are interspersed between layers of soil that are wrapped into natural geotextile materials to provide soil reinforcement. The matting provides erosion protection for enough time to allow the vegetation to establish and bind the soil together. So this is probably my favorite technique. And finally, vegetated timber crib walls that consist of a hollow box-like interlocking arrangement of structural timber. These boxes are then filled with suitable backfill material and layers of live cuttings. It is the intent in this technique that the vegetation will be fully established and take over the role of erosion protection by the time the timber degrades and is no longer providing structural support. Just wanted to point out that I believe that each of these techniques has been used in the southern Alberta, definitely within Calgary. A presentation by an engineer is not complete without some numbers. So here is a table that shows the permissible velocities and shear stresses for some native materials and some bioengineering techniques. The velocities shown here give an indication of the capacity for resistance to fast flowing water, and the shear stresses give an indication of the force that the material or technique can withstand. So essentially, the higher the velocity or shear stress that's shown, the more robust or strong the material or technique is. Now, these numbers can then be compared to the analysis of expected velocity and shear stress at the site that are developed during the site assessment or site investigation, so that the appropriate technique can be selected. So of interest here is that a number of the techniques can withstand about the same velocity as a 300 millimeter average diameter riprap, which is about a beach ball sized rock or class 1 riprap. And some techniques that provide about the same shear stress resistance as 450 millimeter average diameter riprap, which is close to a class 2 sized riprap. So now I'm going to go in a little bit more detail to the techniques that we're using at the West Bragg Creek project. We're using 4 different techniques to attempt to revegetate the eroded or vegetated areas. I've included the details from the engineering drawings on the right-hand side of the slide here, and then some photos of each technique. So the first technique is live staking, which consists of inserting dormant live cuttings into the ground at approximately 75 to 80% of their length into the native soils. While some guidelines say that you can pound the cuttings into the ground, my preference is to create planting holes with rebar or an auger and push the cuttings into the pre-made holes. And the length of the cuttings is typically 0.6 to 0.8 meters, where I believe we're using 0.6 meters for the West Bragg Creek project. This is one of the simplest bioengineering techniques, and it allows a deep burial of cuttings to access soil moisture. However, there's often a low survival rate that we are still investigating as part of the repair monitoring program. Basically, suffice it to say that we've started to recommend spacing cuttings closer than the 1 meter that's previously often specified. We appear to be seeing better results with spacing at 0.3 meters to 0.6 meters. This is what live staking might look like during and after construction. The photos on the left, both the top and bottom, show two different planting hole making techniques. Up in the top left, they're using a hammer drill with an auger bit, and they're using a steel bar in the lower left. The upper middle photo shows how a planting hole is recommended to be closed with a slurry of water and soil, with soil amendment in the hole as well that we'll discuss later. We want to make sure that there are no air pockets left around the cuttings. A finished live stake site is shown in the top right, and a photo of the same site 3 years later is shown in the bottom right here. Note that the cuttings have grown upwards of 2 to 3 meters tall. The spacing at this live staking site at the Bioengineering Demonstration and Education Project is 0.3, just for reference, 0.3 meters. The second technique that we're using at the West Bragg Creek site, this is at Area A, is brush layers. Typically, brush layers consist of dormant live cuttings that are placed in a crisscrossing or overlapping manner between layers of soil, with the tips protruding beyond the face of the fill. We are doing it slightly different at the West Bragg Creek site because to install a brush layer, according to what I just said, we'd have to excavate a relatively deep trench, and we are attempting to avoid any large disturbance or excavation for this project. Brush layers are a very good technique for dry sites as the cuttings are deeply buried and they're between 1 meter to 1.5 meters long. So there's more soil around them to access moisture. Survival is typically okay based on the results of the riparian monitoring program at around 65%. One reason for slightly lower survival than a typical target of around 70 to 80% survival is that the angle of the brush layers was traditionally very flat at around 10%. A steeper slope allows the cuttings to access deeper and likely more moist soils, such as what we're planning to do at the West Bragg Creek site, where we're installing them at a 1.5 to 1 slope. Also, sometimes the ends of the cuttings were extending beyond the recommended burial of 80% or 200 mils, and the cuttings were too exposed and were drying out. For this technique, I'd recommend to have a spacing of, I've seen, or it's recommended to have a spacing of 10 to 20 cuttings per linear meter. However, I've seen anywhere between 5 to 20 cuttings. The close spacing seems to help the willows grow, mostly based on observation. This is a total hearsay, but it seems that willows like to be planted in a community with close neighbors, which may be why the closer spacing for the live staking technique seems to work better. Here's some photos of the brush layers before, during and after construction. The photos on the top and middle right show, firstly show heavy equipment excavating a trench for the cuttings, and then secondly, live cuttings being placed in a row at 10 per linear meter. There's also a container plant added to this brush layer to make it a new technique called a hedge brush layer. They're very similar. The difference is that one container plant's added. The container plant's added for species diversity so that fruiting shrubs and nitrogen fixing shrubs can be used since they don't tend to root from cuttings. The photo on the upper right is more of an example of what we'll be doing at West Bragg Creek, where the cuttings are spaced a little further and installed in planting holes. We will, if they extend this far out of the bank, we will trim them to be about 200 mils or so exposed. The lower photo shows the hedge brush layer at the Bioengineering Demonstration and Education Project 3 years after construction. The brush layers are providing excellent cover and have grown to about 3 meters tall. Both the bottom photos are from the demonstration project. The third technique is a fascine at Area 3. A fascine is a 2 to 3 meter long cigar-shaped 200 millimeter diameter bundle of live cuttings that is placed on contour. There's usually somewhere in the range of 10 to 20 live cuttings to make up a fascine. And then the cuttings are cinched together with a rope to make the cigar shape. And then they're placed in a shallow trench and covered with and infilled with soil and anchored in the trench using wooden stakes. The ends of fascines should be interlaced with the next fascine down the contour. They're used on slopes to provide a physical barrier that's slow runoff and trap sediment. Then when the live cutting is established, the resulting vegetation helps to reduce soil moisture and provides further erosion protection. As I mentioned, they are installed on the surface, so they don't have deep access to soil moisture. So for this reason, they should be used on moist, slightly shady and or north or on the appropriate aspect. Based on the data from the riparian monitoring program, the survival for this technique is around 85% or so, which is quite good. Here are some photos of fascines during and after construction. The photo in the top left shows the fascines getting built on a bench. Unfortunately, we won't have such fancy equipment when we're working on Friday. The top, middle, and right photos show the fascine getting installed in the shallow trench and then covered and filled with topsoil, mostly covered. The bottom left photo shows the contour fascine 3 years post-construction, and the bottom right shows a close-up of the fascine and several stems growing out of it, where you can see that it's establishing quite well. The final technique that we are using at the West Bragg Creek site is container plantings, which are being used as ground cover to control erosion, to provide habitat and enhance aesthetics. They're being planted up on the bench outside of the flowing water zone of the creek, of the Bragg Creek. Plantings have a higher survival rate than live cuttings at 95% versus 68% for live cuttings in Calgary. So you might ask, why not always use container plants for bioengineering? The key reasons are that they are more susceptible to erosion than live cuttings, since their roots are buried relatively shallow compared to a live cutting. So they're typically not used in locations where there's flowing water. So that's, as I mentioned previously, where they're located on the top of the bank here for the West Bragg Creek project. Also, a key advantage of the live cuttings is that they act a bit like soil nails and provide additional soil stability versus what a container plant can provide. Plantings are typically more costly to purchase and install than live cuttings, especially if the live cuttings are harvested at the site, in the case of what we're doing, again, at West Bragg Creek. So one way of getting around the lower survival is to plant more live cuttings, since they are cheaper than plantings. Here are some photos of planting installation and post-installation. The top left photo shows some container plantings at a construction site. The middle, I believe those are 1 gallon containers. The upper middle photo shows a skid steer with an auger attachment that's digging holes for the plantings, similar to what was done at the West Bragg Creek site. And the top right photo shows, although there will be some additional digging on Friday, the hand digging, that is. The upper middle, the top right photo shows the container plants being installed in the auger planting holes. The photos along the bottom show how a planting site looks 3 years post-construction. Container plantings may sound simple, but as this figure from Agroforestry and Woodlot Extension Society of Alberta shows, there are 9 common issues for plantings that have been identified and only one right way to do it. So there's planting too deeply or too shallow, leaving air pockets around the planting, creating a planting hole that is too shallow or too narrow, which results in L, J, compacted or tilted roots, leaving soil too loose around the planting, and planting in poor quality soils are all issues to look out for when installing container plants. So here's some photo evidence of plantings that were not installed properly, where the planting hole was too shallow and the roots at the top are exposed. Live full drains are not a technique that is part of what we'll be doing at West Bragg Creek on Friday. However, it is a useful technique to know to manage excess moisture from a site. Live pole drains consist of a long cigar-shaped bundle of live cuttings that are oriented downslope. They use basically the same materials as a fascine, except that fascines are installed on contour, and the live pole drain is oriented downslope. They work by providing a preferential flow path for soil moisture, and then when the live cuttings in the bundle is established, the vegetation further reduces soil moisture through evapotranspiration. Live pole drains allow a variety of shapes, since they are constructed in a modular fashion, with each bundle or fascine at about 2 to 3 meters long. Here's some photos of live pole drains taken from the City of Calgary Bioengineering Design Guidelines. The photos on the top and bottom left show the downslope orientation of the drain, and also some lateral drains that are connected to a main central drain. This illustrates the flexibility of the technique to cover a large area of moist soils. The bottom right photo shows the same site about 2 years after construction. So the vegetation species that we selected for the work at the West Bragg Creek site were based on a riparian health inventory of the old Shell Road Bragg Creek reach that Cows and Fish conducted last year. The inventories of cows and fish that Cows and Fish produces are invaluable resources for designing bioengineering projects. And if you have access to one, definitely refer to it for your site. Other resources to consult might be your biologist team member, the Agroforestry and Woodlot Extension Society Native Agroforestry Species Database, or the Alberta Biodiversity Monitoring Institute mapping portal. I'm sure that Catherine or Amy or other Cows and Fish staff or other attendees would have suggestions here as well. So when it comes to container plants, the species we selected for the riparian planting at Area 1 were Bebb's willows, Canada buffaloberry, northern gooseberry, prickly wild rose, shrubby cinquefoil, silverberry, and white spruce. With respect to live cuttings, we'll be looking to harvest live cuttings at the West Bragg Creek site from native stands of balsam poplar, Bebb's willow, flat-leaved willow, and smooth willow. And I'm excited here to be using two new species. There are two species that are new to me. So the flat-leaved willow and smooth willow to see how they perform from cuttings. We should definitely get the best results using the poplar, Bebb's willow, and flat-leaved willow, as they are all known to root readily from cuttings. Smooth willow may not have the same ability as the flat-leaved or the Bebb's willow to root from cuttings, so we may limit the use of that species depending on what is available at the site. The next few slides cover the best practices for live cutting, harvesting, handling, and installation, and are basically the nuts and bolts for how to do bioengineering using live cuttings. So starting with live cutting harvesting, so you need to obtain permits, authorizations, or permissions from the landowner if you're going to go out and harvest cuttings. It's incredibly important to harvest when vegetation is dormant, so during the dormancy period from October 1st to March 31st. They want to harvest from sites with comparable site conditions, hydrology, landscape position, elevation, with similar species with healthy stands of native vegetation. You want to avoid rare or sensitive habitats. It's important to confirm the species prior to harvesting and store those species in separate piles so that you can, you know what you're going to be installing later on. You can also paint the tips, and that helps to identify species and also to reduce desiccation post installation. So this is optional, but it is recommended. Choose healthy stems that are 1 to 4 years old with diameter between 2 centimeters at the tip, and we'll leave that to your imagination. No kidding, it's between 2 and 4 centimeters or so. Avoid diseased material and dead stems. You want to select relatively straight and smooth stems. Harvest at most 1/3 of the native plant. Do not ever clear cut your donor sites. You want to harvest live cuttings using chainsaws or loppers as close to the ground as possible with clean cuts. You want to cut the butt end at an angle and the tip with a horizontal cut, and then hand prune all the limbs off without damage to the bark. So they should look a little bit they should look like the picture on the bottom right here. Depending on the length, it could be quite a bit longer though. For live cuttings, handling and soaking, you want to limit the amount of time between delivery and planting to 1 day if possible. You do not want to damage the bark or during transport and handling. You do not want to expose live cuttings to direct sun and heat, so you cover them with a tarp, either wet burlap or a silviculture tarp as shown on the top right, and keep the cuttings cool. For indoor cold storage over long periods, you want to maintain the temperatures at a minimum of -2 degrees Celsius. For soaking, you soak cuttings in fresh, clean water for a minimum of 1 week to maximum 2 weeks prior to installation, or 2 days if pre-harvested on site, or install immediately after harvest. And it's important to submerge 75% or in that range of the length of live cuttings when soaking. And also to cover the cuttings on site and protect from beavers so they don't steal your materials. So now if there's anything to take away from this webinar today, it's that installing live cuttings when they are dormant will increase the chances of success for bioengineering project. To illustrate this photo here shows a section of timber crib wall where live cuttings were installed in August, outside of the live cuttings dormancy period here on the left, and live cuttings that were installed in April within the live cuttings dormancy period on the right. There are hardly any live cuttings still alive on the left, but on the right, the vegetation is establishing nicely. So to further illustrate this point, we've developed a recommended planting schedule as part of the riparian monitoring program as shown in this table below. Recommended planting periods are provided for native plant seeding, container plants, and live cuttings harvest and installation, and most recommend to not plant within the mid-July or mid-June to end of September window. Planting outside of what is recommended here may be successful in limited circumstances, but there's significant risk of failure, and so limitation of work in this period is strongly recommended. So in summary, plant live cuttings harvested in spring before the 3rd week of June. Plant live cuttings harvested in the fall, either in that same fall after soaking or in the spring after storing in cold storage over winter. Do not use cuttings that are harvested in the spring and stored over the summer for fall planting. That's a recipe for low success. Use tall rootstock as an alternate if construction is scheduled from the 3rd week of June to October. So there is some flexibility in that period between mid-June and September. When it comes to live cutting installation, we want to create planting holes with a steel pilot bar, rebar, stinger, or hammer drill. We want to make sure that our live cuttings are in the ground at least 80% of their length with basal end first, and default at maximum of 200 mils. Prevent stripping of the bark, damaging the buds, or splitting the cuttings during installation. You do not want to leave air pockets or voids around the planted live cuttings. So one way to do that is to backfill the planting hole around the live cutting with soil amendment, followed by a slurry consisting of topsoil and water with the consistency of thick syrup. So as I mentioned previously, you want to leave a maximum exposed length of live cutting of 200 millimeters, and it's okay to trim them if necessary. If live cuttings are damaged during installation, including any cracks, you want to prune off that damaged portion of the cutting to reduce the occurrence of disease or pest entry. And then you want to water those installed live cuttings thoroughly. So other key installation considerations that we've identified through the repair and monitoring program. For one, fencing for wildlife and humans has a statistically significant positive effect on the survival of live cuttings. Additionally, the use of soil amendment has a statistically significant effect on the growth of planted vegetation. Mean shoot length is statistically higher when soil amendment is used versus when it's not used. So what I'm referring to here in the soil amendment is the specific recipe that's found in the Calgary Bioengineering Design Guidelines that is composed primarily of peat or compost, 444 organic fertilizer, humic complexes, and endo and ectomycorrhizae. We're going to be using a different recipe for soil amendment at the West Bragg Creek project, which I'm excited to see the results of using that one. We've also identified that soil compaction has an effect on planted vegetation growth. We've found that the larger the depth of uncompacted soil, the larger the growth of the planted vegetation. This result points to the need for more care during construction so that equipment or foot traffic does not result in soil compaction, or the need to decompact the soil at the end of the project if equipment use is necessary. Irrigation has been observed to support vegetation establishment and is a must in Calgary due to the air climate and the warm winter conditions, the Chinooks that blow through. Weeding of invasive species helps to remove the vegetation that could overwhelm a site and outcompete the desired vegetation for nutrients and moisture, effectively killing the planted vegetation. And now the same is true for high rates of seeding, which we've observed at several sites in Calgary. Temporary erosion and sediment control measures provide stability and protection against erosion to allow vegetation to establish. Once that occurs, the erosion and sediment control practices job is done. So it's important to select products that last long enough to allow the vegetation to establish, but then it's also important to consider the long-term implications of product choice. So if the material will not be removed from the site, except under limited circumstances, it should not be synthetic, as plastic mesh causes hazard to wildlife, as mentioned previously. Public education via science or stakeholder events will help to inform the public about the purpose and the importance of the work that is occurring. And hopefully these efforts will lead to the public embracing and protecting the site versus the opposite. Once construction is complete, the emphasis then switches to observing, maintaining, and correcting any issues at the site. Monitoring and maintenance program should run between 2 to 3 years post-construction to give the vegetation enough time to establish. A typical program would consist of irrigation, weeding, and repairs, and minor repairs to fencing, erosion, etc. As mentioned previously, fencing is very important through this time as it keeps wildlife, particularly beavers, out of the site, since it would otherwise be a veritable beaver buffet, and the plants aren't typically strong enough yet to withstand heavy browsing. But they're also there to keep humans, dogs, vehicles, etc. out of the site, since foot and animal traffic will compact soils and damage plants. Now, as part of the repair and monitoring program, we've collected growth data by species for over 6,000 live cuttings and plantings. This data will can help give an indication of expected growth for planted vegetation. The table here shows several species that we have included in the design at the West Bragg Creek site and what we might expect for survival, leader growth, shoot growth, and diameter for year one growth post-construction. So this could help to identify the trajectory of the site, identify the trajectory the site is on, and then help to identify remedial measures, if any are needed. So now in summary, here are some key messages. It's important at the very beginning of the project to develop clear project outcomes. So an example could be that the objective of the project is to stabilize the site from erosion and improve riparian health. Next, it's important to understand the site and what is driving the erosion processes that are occurring. We need to select vegetation species that are native and local to the site that can root from cuttings if live cuttings are to be used. Harvest or purchasing, soaking, storing, transporting, and installing the vegetation species according to best practices should be followed based on what's presented in this presentation. And that includes installing vegetation during the dormancy period in big bold letters to give the planted vegetation the best start possible by planting it correctly. The great way, not one of the 9 incorrect ways, using soil amendments that have proven to improve growth and or soil survival, protect it with fencing from wildlife and human activities, and water the plants thoroughly at installation. Then we need to keep the vegetation happy until it properly establishes, which is usually 2 to 3 years, by protecting it with fencing, continued watering, and weeding out competing plants. So all of the above will help to achieve a successful bioengineering project. So here are some books and manuals that I've referred to in this presentation, or that are key references for bioengineering. Additionally, there are some links at the bottom of the slide to the City of Calgary Riparian Areas in Calgary website, where some information on the riparian strategy and riparian action program are shared, and also some results from the riparian monitoring program are shared there. And a link here to the City of Calgary's bioengineering demonstration and education project website, where there's a whack of technical information shared on the project, including technical reports, design drawings, and monitoring reports. Just looking at time, I realize it's 1 o'clock. So I do have some case studies to go through, but wanted to get some feedback as to whether we should go to questions at this point or go through some of these case studies. Maybe Amy or Catherine or John from Cows and Fish.
Yeah, hi Mike, Amy here. I see we got about, there's quite a few questions. So far it looks like 7, some having to do with just specific things you addressed in the presentation thus far.
Okay.
So up to you if you prefer to answer them now, or if you want to jump to case studies first.
Why don't we just do quickly the Bragg Creek ones, and then, well, there's some other ones that I have that I can present. If I can do this quickly, maybe it's just a 5-minute thing, and then we can go to questions.
Sure.
So basically, at this point, we thought it would be of interest to review some common drainage and erosion sediment control issues faced by Bragg Creek Trail. So starting with dealing with where trails intercept seeps and springs. So an example of some past bioengineering project work is shown in the photos here, where the photo on the left shows a drainage ditch site in 2019 along a wide trail where water from seeps is intercepted by this ditch and then flows down slope. The photos on the right show the result of what I understand to be several Elbow River Watershed Partnership, AEP, and Bragg Creek Trails projects to improve that drainage ditch, reinforce the slope, and install willow cuttings, install small live smiles in the ditch. Flex MSE bags planted with willow stakes were also used, as were native seeding on the tread and slope. It appears to me, anyhow, that the site is looking quite good, and the appropriate techniques were selected to address the erosion processes occurring at the site. So I just wanted to commend the volunteers and the staff who worked on this. Perhaps other techniques that might be useful to consider on a site like this could be a live pool drain or fascines on the slope to control soil moisture that were mentioned in the presentation, or maybe live silt fences in the ditch to slow and filter runoff along the drainage ditch. A second drainage and erosion and sediment control issue faced by Bragg Creek Trails, a common one, is controlling erosion at bridge crossings. So now the photo on the left shows a new bridge crossing that was constructed in 2015 with exposed soils and a silt fence for temporary erosion and sediment control. The photos on the right show the results of several Elbow River Watershed Partnership, AEP, and Bragg Creek Trail projects over the years, where live staking was installed, as well as transplants of spruce and alder. They also spread wood chips over the live cuttings, and there's a live pole drain in the drainage ditch upslope of the creek. Again, the volunteers who did this work should be commended for their work at the site, as the techniques that were selected should provide appear to be establishing quite well. Some other techniques that might be useful to consider at a site like this would be to place some rock at the toe of the bank to protect against bank erosion or toe scour if the stream bank has been disturbed or narrowed to accommodate the bridge abutments. Vegetated soil wraps with brush layers could be used to rebuild the bank if fill is being placed around the abutments, since the soil wraps are very flexible to construct to meet steep slopes or transition back to native or flatter slopes. or perhaps a brushlet mattress could be placed on the native bank if the soils are exposed and the aspect is favorable. A few other case studies that I've been directly involved with. This first is on the Elbow River in Calgary. There was moderate bank erosion here in the 2013 flood, but there was still quite a bit of native vegetation on the bank here. So the purpose of the project was to stabilize the eroding bank and fill in this erosion feature up in the top right to protect an adjacent regional pathway and park area. So what we did here was to design our approach was to repair that small slumped area with a rock toe, then a brush layer and a live staking above that. And then we put live staking to supplement the existing vegetation on the bank for about 80 meters upstream. So the idea was really to limit the disturbance to the existing vegetation that was well established and to fill in empty spaces with the live staking. We used between 3 and 5 live cuttings were installed in each planting hole. And so that kind of in an attempt to benefit from what I mentioned earlier as willow's preference to be planted with close neighbors. The terrace was also planted with native riparian species and fenced to reduce human and dog traffic. Overall, the brush layer did okay. There was high mortality, but there was high mortality of the live staking. And we attributed this to poor live cutting, handling, and storage practices at the site, where the live cuttings were left out uncovered, they were not properly soaked, and the planting holes were not properly backfilled. So there were large air voids and the cuttings dried out. Also, the vegetation establishment on the bench is not great due to very high compaction. So at this site, while the approach to supplement the existing vegetation seemed to be a good one, the implementation at the site was not amazing. Also, I would have, reconsidering the site, I would have potentially used branch packing as the technique to fill in that slumped area. The next case study is on Nose Creek, where an eroding bank was impacting an adjacent regional pathway as the pathway came down under a bridge. The goal of this project was to stabilize the bank and repair the regional pathway. There were 2 design approaches at the site. The first was a vegetated mechanically stabilized earth wall, or MSE wall, and the second was a vegetated soil wrap. Live staking was used in the MSE wall, and brush layers were used between the soil wraps. The bench above the bank was also planted with native shrubs and seeded. The brush layers at the site are establishing very well, with about 3 cuttings per linear meter that are growing. The live staking in the MSE wall and the plantings of the bench aren't doing as well. There was a very high mortality of the live cuttings in the MSE wall, likely because the fill material in the wall was highly compacted and limited root growth. The reason for the high mortality of the plantings on the bench is not known. It could be lack of irrigation or heavy competition with the grass species there. A key learning from this site was that the brush layers were a good technique again, because they were deeply buried and could access soil moisture, despite that the site had a dry aspect. Another key learning was that establishing live cuttings in a highly compacted backfill that was required to meet the specifications of an off-the-shelf product is next to impossible. And another approach should be used if this technique is used again. I do have 2 other product examples, but I think I'll skip those unless there's extra time at the end for the questions, just to make sure we do have time for discussion. So at this point, maybe we'll have some conversation or discussion and questions, but just to note, my contact information is here if you'd like to reach out. So thank you.
Thank you so much, Mike, for sharing all that information. Looks like we do have about 9 questions. Before you get started, 10 now, before you get started on that, I just wanted to give a quick thank you for Catherine Hall and Jonathan Ferns. Both of them are with Cows and Fish, and they've been working behind the scenes and organizing a lot of this and making it all to come together. So although you don't see them maybe on your screen as floating heads, they are here with us now, and they have been doing an excellent job on keeping this project afloat. So thank you very much. And with that, we'll move to some questions. So I'll just go through the questions as they appear. Mike, can you please repeat what you said about the roots growing around the rocks and the misconception that roots will displace rocks?
Sure. So the species that we use for bioengineering, there's actually a term for this property, but and what I showed in this picture, I'll go back to it here, but I guess I come to think of it, I didn't explain necessarily what you were seeing in depth, but that's an excavation of in a vegetated riprap bank. Oh, there we go. this bottom left corner or left picture here. So that's an excavation of a Beb's willow or balsam poplar, one of the two of them, in a riprap bank. And so what this picture is showing is that as the rocks were taken off of the root structure, you could see that this very narrow gap. Maybe I can try to show you. I don't know if you can see my mouse or not. Is it possible to see my mouse? Okay, good. So that narrow gap here, there's a very narrow spot between two rocks that the willow root made its way through, and you can see how small that piece of root is in comparison to the rest of the root. So basically what I'm trying to show here is, and what I'm trying to say is that observations of excavation of willows and poplars in riprap show that the roots will deform to make their way through narrow gaps versus maintain their same size and displace the rock. Hopefully that answers the question there.
Thank you, Mike. Next question, is there anything that can be done for a very steep and sandy bank?
Yes, there is. That would be, like, sandy bank is one thing that you'd be concerned about. There is, well, two things would be, it's highly erodible material, and secondly, it's really free draining. So which really you'd want to stabilize that material, or that native bank material, by covering it with something and not allowing it to be exposed to erosion. And then firstly, and then secondly, you'd want to put something there that would retain that soil moisture so that you can get something to grow. I wouldn't advise putting something like a live stake into that, because of what I just said, basically, that the live stake doesn't necessarily protect the surface. Live staking, that technique, doesn't necessarily protect the surface from erosion unless you do it really intensely. But even then, with such low soil cohesion and sand, it will potentially flow around those cuttings. And then, and then you'd also be worried about the moisture conditions in that sand. So what I would do instead is I'd build something on the face of that, more so something, a retaining structure of some description, whether that's soil wraps or timber crib wall or something of that nature. Maybe even a live slope grid, since you're looking at a steep slope. Okay, next question.
Is it true that dormancy has not fully set in until the leaves fall off?
I may defer that question to someone from Cows and Fish. My understanding is it's more, I can't tell you exactly when that dormancy period happens. It's why it's kind of early beginning of October, end of March. I think that's the safest. So if you're looking to harvest earlier than that, then you may want to consult a biologist to do that. And I think, in my experience, not all the leaves do fall off of trees and shrubs. So, but is there anything that either anyone from Cows and Fish, Amy, John, or Catherine, do you want to add to that?
Hi, Mike. Yeah, this is Catherine. I just say it really depends on where you are as well, because obviously there's going to be a different growing season depending on where you're working and which subregion, natural subregion we're working within. Yeah, I think generally we've been done projects fairly successfully using willow cuttings in the eastern slopes area, so West Red Creek area, and beginning even in September onward. So yeah, I think once you do see that the plants start to change color, that's an indication that they're entering dormancy. But I think the growing season really will depend on where you are, and then speaking to some of your local botanist ecologists will help as well to help determine the best period.
Thanks, Catherine. Next question says, thanks for the presentation. Question about brush layering. Specifically that's planned for the West Bragg project. How do we make a horizontal hole into the bank? How does one fill the staked hole with soil amendment when the hole is horizontal?
I'm just bringing up the design plan here. So just wanted to point out that we're not planning to build a horizontal hole, but absolutely, if we were doing a horizontal hole, that would be a real challenge to get anything liquid, such as the slurry that we're talking about, to get to flow in. to that hole, but we're actually planning to construct these on an angle, basically perpendicular to the bank as shown here, but that's roughly a 1.5 to 1 slope. And so what we're planning to do then is to use rebar, pound the rebar into the native bank, or use the soil, use an auger that may be both available on site. Pull that rebar out, put some soil amendment in that hole, and then put the stake in. Hopefully the hole is big enough and there's not snags as the cutting gets placed in that hole, and then and backfill the rest of the hole with this slurry. So whether it's a spout, a spout on the jug that we can pour the material in there, and then we'll poke it in with a dowel, or if there's or we use a funnel of some description to pour that material in there to fill those voids. But that has been successfully done in the past for sure.
Thanks. Question. I'm wondering if you have planted stakes into the compost-filled socks.
The short answer to that one is that I have not done that before. But one, I guess I might want to know a bit more about what was proposed there, or what was done in that idea. But the one thing that, at least the picture that I showed of the compost sock, it is the sock itself is a synthetic material. So typically I would like to see those removed once the vegetation is established and there's no longer a need for temporary erosion and sediment control. So planting through that particular material, I wouldn't necessarily want to do. But if there's if there is a biodegradable sock, yes, you could plant through that. One concern would be to make sure that you have enough of the stake deep into the native bank, native material below that, so that it's hard to predict what the temperature regime or the moisture regime will be in that compost sock. So I would try to get as much as I could below into that native material, and rely on that for the growth, where the part through the compost sock would be more potentially for stabilizing that, as a method to stabilize that compost sock in place.
Thanks. Next question. Have you ever used bioengineering and/or living structures on a lake shore, or to replace an existing wooden retaining wall?
I'm currently working on a project where we are doing that. It's the main concern and the main difference between riverbank or streambank slopes and lakeshore. This lakeshore gets wave action, and depending whether that's because of a long fetch and wind action, or if it's a lot of boat traffic in the lake. So the situation we're working in is there's a lot of boat traffic, and that's causing a lot of wave erosion. So what we're doing there, we've come up with a couple of options. One of them is a brush mattress, and the idea with the brush mattress is that it can, because it's placed along the face of the slope, it can withstand a lot of fluctuation in water level and still have part of that live cutting outside of the water level, or outside of the water, exposed from water, I guess is what I'm trying to say. So so that's one option that we've come up with. We do have some, there's some special considerations there around making sure that the material that's placed around the live cuttings doesn't get sucked out as waves recede and are washed out. So that's one thing. We've also done, or I think what we're probably going to go with is a vegetated riprap approach there. So we'll be putting in brush layers amongst riprap. And so then, rock is a pretty tried and true method to stabilize or protect against erosion. And we're, putting in some brush layers there to vegetate that. And also, the vegetation, once it grows, those roots will tie those rocks together and tie into the native bank. So next question, Amy.
What sampling protocols did you follow to derive the stats, i.e. plots, subplots, etc.?
So there's a whole monitoring protocol that we've developed for this project, of which Catherine Hull from Cows and Fish was involved with. For survival, I don't remember if I think the survival is from the pinpoint transects. So there's three methods. There's the survivability assessments that where someone's going and counting plants and along a transect and seeing which ones are alive, which counting alive and dead. We were also doing pinpoints as part of the transect. It's a pinpoint transect, so and that's when we're measuring cover. Quadrats, so that's looking more so at vegetation cover, herbaceous cover. If there's a whole, it's a scientifically based program with very detailed protocols for field data collection and also for analysis of that data. If you're more interested in that, I can certainly share information. So just maybe get in touch with me and I can provide more information on that, those protocols from the riparian monitoring program.
I would just say, Mike, maybe you want to just touch on the protocols also designed so that you're looking at projects in different age classes. So
right.
Projects that were like 1 year post-construction versus 3 versus 5 year and older. And that we did develop a sort of a topology ahead of time, especially with the bioengineering type of projects that was based on a vegetated versus a kind of non-vegetated gradient, right? So that was also an important piece of that, the statistical protocols that were developed, where it was kind of that stratification of the project types and categorization of that, and then making sure we've got adequate sample size of the different age classes as well.
Yep, very good. Thanks for that, Catherine. That's it's a the riparian monitoring program is a wonderful project. There's a lot of data that's coming out of that. A lot of it is from what we understand is new to the bioengineering community. Like so the table that I presented with growth parameters, for example, is not something that's been seen before. So we're very pleased to be involved in that project and to have people like Catherine and Alan Dodd, who you all might know as well, and Pierre Raymond and our colleagues from INRAE in Grenoble, France, Andre Yvette, etc. So, but that's a more deep conversation for maybe another time to talk a bit more about that program. Next question, Amy.
Okay, we got a couple questions from Joyce. So the first one, she says, thanks so much, Mike and Cows and Fish. Mike, can you share your thoughts on root wads and when it might be suitable to use them? And she mentions that she's working on a offsetting project on a pipeline.
Okay. So I really like root wads. They provide great in-stream habitat. They also provide, so that's if you're looking at putting them in a stream or creek. I also like them placed on the bank or in any, for example, if we're doing a rough and loose treatment, placing them randomly around to provide wildlife habitat and they biodegrade and provide nutrients for soils. So yes to all the ways that root wads can be used. That said, if they're being used in flowing water or near a creek and that, it's important to make sure that they're either anchored properly or that it's okay if they float and make their way downstream. So there's a whole design approach to dealing with cuttings. So, pardon, not cuttings, live with root wads. But ultimately, if there's examples of them, and I've unfortunately had to do this too, where they're placed quite high up the bank, and they provide pretty limited fish habitat if they're high and dry during normal flow conditions. So I would make sure that if you're putting them in, you try to get them as low as you possibly can, and make sure that they're the rule of thumb is 3/4 if you're burying them in the bank, 3/4 buried, and with enough ballast over top of that, soil ballast over top of that log, that they won't pop up and float away on you in a flood situation. Next question, Amy.
Okay, another question from Joyce. Is there any benefit to dipping live cuttings on one end in wax to help minimize moisture loss?
It seems a similar approach to painting them. The paint that's used on the tips is typically a 50% latex, 50% water, so it's a watered down version. I can't speak to that. I haven't heard that necessarily, but the principle to minimize moisture loss seems, and maybe using wax is more of a natural product than using paint, latex paint. So perhaps that's where that came from. But I would maybe suggest that getting wax on the end of a live cutting might be somewhat difficult if you're, the installation for these is typically October to, to end of April, Mayish. So it could be a little bit cold. So you're basically going to have hot wax around somewhere. So logistically, it may be a bit of a challenge, but otherwise, I don't know if anyone else wants to speak to that, but those are kind of my thoughts on it.
Thanks, Mike. Question from Greg. Have you or Cows and Fish ever found the proper functioning condition assessment useful when demonstrating results with public or ranchers?
So if I can interpret this, proper functioning condition would be something where this is the way that this system is supposed to function. So you may find an undisturbed section of creek, for example, or an undisturbed slope, and use that kind of as in discussions with landowners. That's kind of my interpretation of that. I don't know. It might be a proper functioning condition is likely a proper term, but I've never used that before. So, but I have used using undisturbed native conditions to inform design, but also to be able to use it as an analog or as a description or a tool to talk with stakeholders for sure. Yeah. So Catherine, Amy, or John, do you want to speak to that one?
Myself, I'm not familiar with the proper functioning condition assessment like that language necessarily. I would agree with Mike when we're typically doing restoration projects that we are looking for what we call like a reference condition, play a goal that you're aiming towards. So what we would call, undisturbed. For Cows and Fish, we do use our riparian health inventory, or a more condensed version of that riparian health assessment, to communicate with ranchers or landowners or land managers the current condition of the landscape or the riparian area, and then we can translate that into what that could mean for changes in management. Catherine, are you familiar with proper functioning condition?
No, I think it's just a language terminology thing, perhaps. Certainly when we do the riparian health inventory, is essentially what we're looking for is to categorize a site as to whether it's ecologically functional. So a site that's ecologically functional would be, categorized in a healthy condition versus an unhealthy or sort of not properly functioning site. So it may just be a terminology thing, but we certainly have our methods are available on our website, or we can certainly provide more information on that after the fact if you do want to find out more about our riparian health assessment inventories and what we look at and what parameters we look at for that. Yeah.
Thanks, Catherine. And lastly, a question from Caitlin. Have you tried cuttings of red oyster dogwood? And have you tried the pollster techniques of using stakes positioned in a tripod to establish shade for fish habitat?
I have tried cuttings of red oyster dogwood. We did not get very good success with using cuttings. And that's not just my personal experience. That's something that's been at least City of Calgary wide experience. And so it's no longer, red oyster dogwood is no longer really recommended to be used as a cutting in the Calgary area. So now we incorporate it as a container plant. So when I was mentioning earlier about hedge brush layers, you can lay out the species of cuttings that form adventitious roots, and then you can plop a container plant for red oyster dogwood, and then that seems to work quite well. We've got good results with that. And so the second question is, I think it's called a live palisade, but the technique where it's a tent or over top of a creek. I have not used that technique before, and getting to, I've only ever seen kind of the pictorial descriptions of that, and I hesitated ever using it because it's getting to some of the nuts and bolts of getting back to the slide on the nuts and bolts of installation we want to make sure that our live cuttings are installed deeply so that, you know, basically 3/4 of the live cutting is embedded in the soil. So what I see in that drawing is that a lot of the live cutting seems to be exposed, and that might work well in areas where there's a lot of precipitation, a lot of soil moisture, where, you know, you're still burying half or so of that cutting. But in a place like Alberta, you know, we'd want to, I'd probably shy away from using that technique. I'd prefer to do more planting along the edge and allow that vegetation growth to establish, and then cover over, as you see in one of my photos here, provide that cover and shade over top of this photo here in the top left, where you can see that's about 2 meters from the bank, that overhanging vegetation.
I will say, Mike, that we did, I think Trout Limited did try that technique that with Dave Polster last fall in the Whitefish Creek watershed, and yeah, had very little success with it. Unfortunately, all the cuttings, like you said, dried and were desiccated. Yeah, I think we're operating in a very different climate from where those techniques may be successful. So perhaps in BC that may work. A lot wetter climate, but in Alberta, like Mike said, it's a challenge because you've got much drier conditions.
Mm-hmm.
Thanks, Mike. And I just, Greg shared the link for proper functioning condition assessment. So I just put that in the chat box for anybody that's interested in exploring that further. And maybe, Catherine, could you pop in the chat box a link to our riparian health inventory? So if anybody is interested in that, they can also take a look. And we are at 1:30, so we have completed all of the questions. Well, I shouldn't say we, Mike, you've completed all of the questions, and I think there was about 10 or 11 of them, so that's pretty amazing. And thank you so much for sharing your knowledge with us and your experience today. I have learned a lot from this presentation. I do believe the recording will be made available. Is that correct, Jonathan?
Yep, that's correct.
All right. And again, thank you so much to Jonathan and Catherine, who have been putting a lot of work into planning of the West Bragg restoration project and coordinating these training sessions. They were also instrumental in organizing the volunteers. We've already done a little bit of work. You might have seen from my opening introduction slides, we had some pictures of the plantings that have been done already. I think it was around 500 or so plants, so that's pretty incredible. And with all that said, I will say goodbye to everybody and enjoy the rest of your day.